Okay, guys, so this is the video that's in lieu of class today. So, we'll get a little bit into this. We're going to talk about organometallic reagents. The basic idea is we're making a carbanion that will attack a highly positive carbon. So, that is then the carbonyl. So we'll go ahead and get started. I'll work off the dock camera so that it's like board work. Maybe not as good, but it will work. We last left off talking about how mainly Grignard reagents, and these guys will act as nucleophiles and bases. These guys are really easy to form. Really easy to form. Most of these guys will form with simply a alkyl halide. The basic idea is, so if I want to make a lithium group, I'm just going to add, for example, two equivalents of lithium. What does lithium have? One electron. One valence electron it can lose. We need two electrons to do this. So we're going to make the byproduct of an alkyl lithium and a lithium halide. So partial positive, partial negative. If I want to do a Grignard, just as easily, if not easier, Rx with magnesium, because magnesium, has two valence electrons. That's going to just insert itself between the alkyl halide. But of course, the carbanion is the less stable of the two, and it's the stronger nucleophile of the two. It's all about strength. Strength of the nucleophile. So, one thing to note is this needs to be done in a product solvent. So, diethyl ether is often the solvent we want to use. If we use a product solvent like water, if we did the basic Grignard in water, all you're going to do is form RH bond and hydroxide. And Mg, 2 plus and X minus. So you're not going to really accomplish what you want. So we got to make sure a product solvent. So diethyl ether. So we want a polar aprotic solvent. Now, organocuprates are relatively easy to make, but they're one step beyond the organolithium. So organocuprates, we're going to take an organolithium, two equivalents, in fact. Take two of these guys and mix it with a copper iodide. So copper 1 iodide. And what we form is R2CuLi. So you get a plus copper iodide salt, and lithium iodide is the byproduct. So it's not super stable, but I mean, it serves as a source of carbanions. Equally, we can make a nucleophile that will work in a similar fashion just from a triple bond, a terminal triple bond. We call it a acetylide. Acetylide anion. So we can make these with a sodium ammonia, sodium amide, base or sodium hydride base. So we're going to use this to deprotonate a particularly acidic hydrogen. Because this guy is particularly acidic, and so in the presence of a strong enough base, so NH2 minus, for example, which is stabilized by the sodium, we're going to then just remove that. Or in the presence of sodium hydride, we're going to remove that. And so you form RC triple bond C minus. And of course, ammonia. This guy can be associated with the salt. Equally, we can do the same with alkyl lithium. Alkyl lithium, because remember, as I said, most of these organometallics are bases as well as nucleophiles. Though we can depronate this to form a acetylide. One, two, three. Lithium, and of course you're just pronating your organolithium. So those are just ways to do this. So the acidity of this is pKa of 25. Remember, our water has a pKa of, well, I think 14. We have a range of 14, so this is a reversible reaction. This is a reversible reaction, of course, but what we know is if this is methane as this byproduct, methane has a pKa of 50. This is acidic and this is basic and relatively. If this is much weaker acid, we always go to form the much weaker acid as opposed to here. So you could think of this is HCl and this is acetic acid. If I put lithium acetate and HCl, what's going to form? You're going to form acetic acid and lithium chloride. You're not going to leave it as lithium acetate. So, here's some basic reactions. Here are some simple reactions where we treat our organometallics as bases. The first is just reactions as bases. So, anytime you have water present, it's going to deactivate these guys because water has a pKa of 14. So this guy, water is typically far. Is only like more favoring the right than it is favoring the left. More favoring the right than it is favoring the left, because, as I said, pKa of 50. Now, am I going to ask you to memorize these pKa's? No, God no. However, this is for reference of why this reacts. High peak or low pKa, high pKa, it's going to go to the right as opposed to go to the left. Does it mean we can't go to the left? No, it's just the equilibrium lies more heavily to the right. In the presence of many alcohols. So, like, for example, if I use phenyl magnesium bromide in the presence of methanol, it's going to form just benzene and methoxide, a methoxide anion. So if we want to make a certain base, very basic, we can do that with many of these. In any presence of carboxylic acids. So, like, say, let's do methyl lithium, carboxylic acid, so like acetic acid in this case. We're going to have methane again and a carboxylate. So, don't be too surprised if that's what you have. Don't be too surprised if about forming these guys. Make sure we know what we're putting in these before, what conditions we have before we do this, or else this is what the product we're going to get. Now, what's more important is the reactions as nucleophiles. So our reactions as nucleophiles is where we're going to really use these. So our typical reaction is conditions are going to be, we use some sort of organometallic, and then work up with water to deactivate this. So generic reaction R, C double bond O, R prime. R prime could be equal to either a proton or some sort of alkyl group. Doesn't really matter. Step 1, we're going to put in typically a different R group and organometallic. M could be lithium or magnesium halide. We don't really care. But step 2 is then we work up with water. The basic product is going to be R, R prime, R double prime, OH. And we're going to get usually a mixture of enantiomers. If we can't control where this is going to attack, this is planar. So it's either going to push that down, push it up. So stereochemistry, we're going to get a mixture of the two products. If we have a substituted, like a carboxylic acid derivative, like Z is equal to chloride or some sort of a ester, and that doesn't need to be minus, we get a different product. So R double prime M, this is going to be interesting, and we'll talk about why. Depending on what we use, we're either going to get R double prime O R prime, or we're going to get R OH with 2 equivalents of our R prime. So either way, the OH function, the oxygen functionality stays on, but whether we have a single addition, a single reduction, or a double reduction depends on the what we add. I think this is the cuprates, organocuprate, and this is our organolithium and Grignard. So these guys are more reactive, and these guys are less reactive, and so they end up stopping. And And another reaction we can do is an extension reaction. We can react with CO2. So if I react with step 1, CO2, and 2, acid, I can get a carboxylic acid. So we've basically slapped a CO2 between these guys and then protonated this carboxylate. Another one we can do under the same realm, instead of CO2, if we react with a epoxide, some sort of epoxide, and work it up with water, we can basically, you're just going to ring open the epoxide and add 2-carbon alcohol into it. So we're going to have added approximately an ethanol onto there. That's going to ring open standard method. For these three reaction types, I mean, with reaction 1, this is similar to for organolithium, and Grignard. These are similar to other nucleophilic addition. So nucleophilic addition. Remember, so we're not replacing something, we're just breaking a bond. So if I have formaldehyde, is going to go to a primary alcohol. So ROH. Let's say an aldehyde will go to a secondary alcohol. So R prime M, secondary alcohol. And a ketone will go to a tertiary. So, alcohol. So we're just looking at this. We have R prime, R double prime, which, if you have an achiral starting material, you'll get an equal mixture of enantiomers. So you're gonna have 50-50 RS mix. If these are all different, 50-50 RS mix. This obviously is no chiral center. But that's because, once again, trigonal planar means the Grignard can attack from the top, it can attack from the bottom of this flat molecule. In fact, you can work your way backwards. A retrosynthetic analysis of Grignard. We can say, oh, if I have a primary alcohol, it converts to a carbonyl. We can figure out what R group we need bound to this. So if I have this structure, and I'm wondering what I'm just looking at generic structure, there's three things here. What would I have needed on the Grignard? Well, I can start with acetone and whatever that R group is. Go, oh, I need, say this is 1, 2, say this is I guess this would be what? If R is a benzene, it'd be the, let's say, what is it? Isopropyl alcohol benzene? I don't know. But if you see that, oh, these two groups, I can do that. Or you could think about, is this what the group is? And then I'm adding a methyl. You can do it a variety of different ways. And you're just looking at, think about what could I start with? What is my starting material? What is my starting material? What can I be adding? Now, as I said, this guy is a particularly strong base. This is a very strong base, and so what do we do if we suddenly find ourselves, I have a acidic proton and I have a carbonyl that I want to see attacked. I have a nucleophilic position, electrophilic position, and I have an acidic position, and I want to preferentially attack in one place. This is where we're going to get to what's called a protecting group. Not sure if you're familiar with this, but a protecting group is a group we are going to add onto a functionality that makes it largely unreactive to certain conditions. It must come off easily. It should be able to put on easily with good yields. So we don't want it to waste our product, but we need a protexon. So whether you have some carbonyls and a NH or OH or C triple bond CH, we don't want those reacting. So we need to protect the group before we can do a react. So acid base is going to be faster and more efficient than the nucleophilic addition. So proton transfers are just too fast. So you'll break it down in steps. Step 1, protect the acid. We're going to add a blocking or protecting group. The point here is that this is no longer active to Grignard attack. Carry out reaction. That's our step 2. And then 3 is remove the protecting group. So bring back our functionality. Now maybe you want to leave this on for several steps if you have to go multiple reactions that this could have. It's called deprotecting. But the idea is that the deprotecting group in certain conditions should come off very easily. One such protecting group is example. So is silyl ether chloride. Or silyl ether chloride. TBS. And so this guy is tert, butyl, methyl, silyether. I'm running out of room. Oh my god, I didn't know about TBS. So, tert, butyl, dimethyl, silyether. So your basic thing is when you do this, you put an alcohol, when you have alcohol, and you mix in TBS, what you get is it deprotonates the alcohol, puts on the silyl group, and the tert butyl, among other positions, it's bulky, it's going to keep things away. We're going to, it's all the positions are currently taken up. It doesn't want to, react. So here's a condition. So what this looks like, TBS, is, so we'll take an alcohol and mix it with, so the tert butyl silyl ether. So we're making a silyl ether. So tert butyl dimethyl silyl chloride. And then in the presence of our our solvent is midazole. Midazole. Sorry, keeps falling asleep. So midazole is a 5-membered aromatic ring that has 2 amines in it. So, and the net reaction produces, our silyl ether. How do we remove it? We remove it with a fluoride salt. The oxygen is particularly strongly binding to the silicon, but you know what's better binding? Fluoride. So remove with fluoride. Fluoride salt. So we're going to use butyl, N-butyl ammonia fluoride. So it's not a T-butyl. There's 4 butyls. It's ammonium, N-butyl ammonium fluoride. So in the presence of this, so you're gonna, oh, okay, here we go. We have the silyl ether. Oh, okay. Well, I mix in our N-butyl ammonium, fluoride salt, and then you reform your alcohol, and you have a fluorosilyl, which we can then separate out and remove. So the point of this is that, we don't want to react with our alkanes. I mean, we don't want to react with our acid. And so how do we take care of that? Okay. But so that's one thing to keep in mind when we're doing reaction 1. Reaction 2, when we're reacting with carboxylic acid derivatives, it's a, as I said, organolithium and organomagnesium are essentially strong reducing agents. Essentially strong reducing agents, even though it's not a traditional reducing agent. They're very reactive, go all the way to tertiary. Go from a RC double bond X, O, X, C, RC double bond O, Z, all the way to a tertiary alcohol. In the presence, but organocuprates, less reactive. R2CuLi will stop at a ketone. So that's why we take the extra step of making this guy and then mixing in the copper, because if we only want the ketone functionality, boom. But so the basic reaction is it's going to just keep going. Now, mind you, we do still have to have two equivalents of our organolithium. Say two equivalents, or two equivalents of our Grignard. But I don't think I'm pretty sure the first edition is slower than the second edition, so it's much easier the second time around to the reaction. So if you don't add the two equivalents, you do not get. You're not going to get like, oh, it's going to stop to a ketone because I only add one equivalent. You're going to get a mixture of products, and so you're not going to get the pure one that you want. So the first is our nucleophilic substitution, and then a nucleophilic addition. Substitution, then nucleophilic addition. There's one problem. So this one, if we're doing this will work with whether Z is equal to Cl or a ester. So, but if we were going with organocuprates with it specifically only will react with acyl chlorides. So we're limited on what we can react with. But you can turn an ester into an acid. So it's just a matter of might have to do some extra steps. So choose what you want to do wisely. So then Grignard will react with CO2, yeah. Yeah, so the basic mechanism for this guy, this is the only one really kind of interesting. All the other ones are X, so got this attacking here, and we're going to kick one of those double bonds up. So mechanistically, we're forming a carboxylate, which is, of course, stabilized by resonance. Pairs in. And then, of course, we just pronate. So, back there, and so we're going to protonate that guy. Go, oh, hey. To acid. Of course, that's going to deactivate our Grignard while we're doing that. Organometallics will also ring open our epoxides. Remember, when we're doing a nucleophilic substitution, a nucleophilic attack. Attack will always on the least substituted carbon. The least substituted carbon. So, we don't have to have a two-membered epoxide. We can have, so, organolithium. So, H, methyl. If I do this, it's going to be, this guy's going to attack what? Right here. Fling that up. And that's going to keep, if that's a chiral right there, that's going to keep that as a chiral center. But this is going to stay chiral. So, jump in the gum. So, edge methyl, then presence of water, we're going to protonate that guy. Methyl. It's a basic step. Okay. Yeah. Okay. Last page of notes, so that's why I'm still pushing through. I know I'm making you sit through a whole class, or just about a whole class. We can also react. This is going to be a thing that's going to come up later. We can have reactions on alpha, beta, unsaturated carbonyls. Saturated carbonyls. And that's due to delocalization. Due to delocalization. Delocalization amongst two sites. Localization at two sites. So, call this. So, we have this guy. It's alpha, beta, unsaturated. We resonate between these two forms. So, we see this form, negative, positive. But resonance also allows us to go to this form. So there's our alpha. And we can delocalize to this form where we have the positive charge here on the beta. So we can see a nucleophilic addition at the 1,2 or the 1,4, depending on how fast we have, depending on conditions. So though it typically sees a tautomerization, as we'll see. So we can see a 1,4 addition. 4 addition. Let's see. Oh, hey, we add a nucleophile. Say, oh, that's going to attack here, and that's going to flip that to put the charge there. So we have, oh, hey, carbonyl, negative charge there, nucleophile. And if the pronation is quick, we form, there's the 1,2 addition. But if we allow this to resonate before we get, oh, minus nucleophile, and pronate would get, oh, here's the enol derivative. However, this will tautomerize, meaning it will rearrange tautomerization. So what it means is this will naturally rearrange into that form, that the enol is less stable than the ketone. And so even if we go that way, see that? One last thing, and then, so organolithium, lithium and Grignard will go 1-2. Grignard will go 1-2 addition. But organocuprates will undergo 1-4. So 1-4. So that means RMGX. If we have that, we're just gonna form so 1 alcohol R. That's our 1-2. But if I have R2CuLi and that same product, we'll undergo the one. We're going to have that product, the 1-4. There's our 1-2. So depending on what we have, what we react with depends on what type of products we're going to get. Okay, that's all. That's all I got. That's the end of the chapter. I want to finish off there. Have a good day.